Okay. So next we'll start the topic bond, anchorage and development length. So basically in case of reinforced structures, what we need to provide reinforcement in the concrete. It means it is not simply like if I just put reinforcement in the concrete, uh, they will attract to each other. No, what we need to develop some kind of bonding, that is adhesive characteristics between the concrete and the reinforcements. Okay, so basically the bond between steel and concrete is nothing but the creation of bonding or creation of adhesive characteristics between the steel and concrete, so that they can act together without any slip. Means either concrete or the steel, no one will slip from one another in a loaded structures when the structure is fully loaded. Okay, so with the perfect bond between steel and concrete, the plane section of a beam remain plane even after bending. So that is the main properties that we can see. The length of a member required to develop the full bond is called the anchorage length. Remember, here it is talking about the reinforcement. Okay, what is the total length of a reinforcement required to develop the full bond is called the anchorage length. The bond is measured by bond stress. So in code books they have given the design bond stress for different grade of concrete. We will see this. Okay, the local bond stress varies along a member with the variation of bending moment. So this bond stress in a particular area is also varying depending on the bending moment. Okay, the average value throughout its anchorage length is designated as the average bond stress. Okay, so how it is done, let us see one by one. Since I am talking about the bonds, so that means there are some kind of bond stress there. Basically what it is said, it is defined as the shear force per unit nominal surface area of reinforcing bar. What I mean to say, what is the total shear force that is acting per unit area of the reinforcing bar we are using? That stress is basically called the bond stress. Okay, if we refer the code book has given the values of bond stress for limiting values of the bond stress for different grade of concrete. How it is given? If you have a code book, you can refer clause number 26.2.1.1. Clause number 26.2.1.1, they have given what is the design bond stress for plain bar in tension. Okay, so design bond stress for plain bars in tension is given in the code book. Okay, how it is given? It is given depending on the defined grade of concrete and the design bond stress. Design bond stress is denoted by tau BD. Okay, for defined grade of concrete, if we have a plain bars in tension, then what is their bond stress? Say we have M20 grade of concrete. I am not writing all, that value is given 1.2. Okay, say for M25 grade of concrete, this value is given in the code book as 1.4. For M30, okay, let me complete it, then M35 and more than or equal to M40 grade concrete. What are the defined value for M30? It is 1.5, for M35 1.7, and for M40 the value is given 1.9. So these are the design bond stress when the for plain reinforcements, plain steel, that is basically Fe250 steel you can say, and when the bar is under tension. Now what will happen to the other case? For other case, if you just refer below, some note is given. It is said for deformed bars, for deformed bars. Basically, we are talking about say Fe 415 or Fe 500 steel. It is conforming to the IS 1786. That is this value will be increased by 60%. That means if you have a tension by reinforcement of Fe 415 steel, the bond stress will be for M20 grade, it will be 1.2 into 1.6. You have to increase this by 60%. Now again it is said for compression bars, if the values or if you are interested to find out the bond stress for compression bars, this value will be increased by 25% for plain bar. If it is a plain bar, that means for M20 grade of concrete, and if the reinforcement is a plain bar under compression, its bond stress will be 1.2 into 1.25. Now if the plain bar if the bar is under compression but deformed bars, then it will be 1.2 into 1.6 into 1.25. okay. So what you can see that it is increasing, basically the value is increasing when, say I am just writing here, deformed bars but under compression. Okay, deformed bars under compression, then for M20 grade of concrete, the bond stress will be 1.2 into 1.6 into 1.25. remember it. Why? This 1.6, 60% extra is for deformed bars, and this 25% extra is for compressions reinforcement. Okay, our basic value is this. So this value is for what? For plain bars under tension. Okay, so this is how we can refer to the code book to find out the bond stress value. Okay, once we know the bond stress, then we can find out the development length required. Okay, so just what is the development length? Let us know that first, then we will see how the development lengths are calculated. Okay, so what is the development length? Let me tell you. Basically, a tension member has to be anchored properly by providing additional length on either side of the point of maximum tension, which is known as development length in tension. Again I am telling, a tension member has to be anchored properly by providing additional length on either side of the point of maximum tension. Okay, in a beam where the maximum tension occurs, on either side of the maximum tensions, what we need to do? We need to increase the length of the reinforcement little bit to create the bonding, proper bonding between the reinforcement and the concrete. That additional length is called the development length. So same thing is also applicable in case of compression member also. We need to provide development length in under compression. Now how to find out the development length? I am not going to details on the derivation of the equation, rather than simply I will be using here the guidelines or the actual equation given in the code books for finding out the development length. If you refer to the code books, you can find out that the equations given for development length is denoted by L suffix d. This LD is equal to phi sigma s divided by 4 tau BD. Okay, LD is the development length. Development length is given as phi sigma s. Okay, this you can get in clause number 26.2.1. Okay, now what is this phi? This phi is the nominal diameter of the reinforcement bar, means for which bar you are talking about, whether it is a 10 mm or 20 mm whatsoever, or whether it is a plain bar or deformed bar, whatsoever, that you have to check. Let's say it is a deformed bar. So okay, just okay, so bar diameter is talking about this diameter, nominal diameter. Okay, then phi s the stress in bar at the section considered a design load. Basically, for limit state method of design, if you are using Fe 415 steel, then what is the stress? We can say 0.87 Fy. So simply 0.5 or Fe415 or Fe250 or 500, whatever the steel we are using. For limit state method, the stress is 0.87 Fy. Okay, so sigma s, basically I am talking about this sigma s is equal to 0.87 Fy. Now this tau BD is the design bond stress, and this value, as already I told you that you can get in the next clause, it is 26.2.1.1. that table already I have given to you. Okay, so that you can use, from there you can get the bond stress value depending on the different grade of the steel. Okay, so that means what it is indicating that for a particular diameter and particular grade of the steel, we can easily calculate the development length, that is additional length required beyond the maximum tension zone. What is that value? Is the LD. Okay. If you refer to the next clause in the code book, that is clause number 26.2.1.2, clause number 26.2.1.2. in this clause it is talked about bundled bars. Bundled bars means when more than one bars are bundled together, in that case how to calculate the development. This equation whatever I have written in the previous page, it is basically for a single bar. Okay, now let's say for bundled bars, I'll just read the guidelines what is given there. The guidelines saying that the development length of each bar of bundled bars shall be that of the individual bars, increased by 10% for 2 bars in contact, 20% for 3 bars in contact, and 33% for 4 bars in contact. That means whatever the individual bars are there, when 2 bars are in contact together, then the development length will be increased by 10%. When 2 bars are there, when 3 bars are there, it will be increased by 20%. Okay, and when 4 bars are bundled together, it will be increased by, development length will be increased by 33%. Okay, so you can refer for this, you can refer to clause number 26.2.1.2. okay. Okay, so next we will see how to provide the reinforcement this development length in case of bars in tensions. Okay, so for that we need to refer to the code book, clause number 26.2.3.3. it is written positive moment reinforcements. Okay, in summary I will tell you what are those things, it is explained there. It is said that at least 1/3 of the positive moment reinforcement in single members and 1/4 of the positive moment reinforcement in continuous members. Okay, first of all it is talking about the simple members. At least 1/3 of the positive moment reinforcement in simple members and at least 1/4 of the positive moment reinforcement in continuous members shall be extended along the same face of the member into the support to a length equal to LD upon 3. Okay, for simple member. Okay, and for basically for simple supported beams it is talking about. Okay, at least 1/3 of the positive moment reinforcement, whatever be the number of reinforcement there, 1/3 at least. Okay, for continuous members at least 1/4 of the members, suppose you have 20 members, 1/4 of the members, at least 5 members should be extended for a length of LD upon 3, whatever the LD required that we have seen in the last. Okay, next, such reinforcements shall also be anchored to develop its design stress in tension at the face of the support when such member is part of the primary lateral load resisting systems. Okay, next, the diameter of the positive moment reinforcement shall be limited to a diameter such that the LD computed for sigma s equal to FD does not exceed the following. Okay, code book what it is mentioned here, I will just let me write the equations and then I will tell you what is given here. Okay, it said that LD in which case when sigma s equal to fd. Okay, should be less than or equal to, or we can say should not be greater than, both are same meaning, m1 by b plus L0. Okay, I am reading the sentence again. Thus, at simple supports and at points of inflection, what is written in the code book, the positive moment tension reinforcement shall be limited to a diameter such that LD computed for FD, that is sigma s is equal to FD, does not exceed m1 upon b plus L0. Okay, where m1 equal to moment of resistance of the section assuming all reinforcement at the section to be stressed to FD. I am reading again. m1 is the moment of resistance of the section assuming all reinforcement at the section to be stressed to FD. What is FD actually? FD is nothing but 0.87 Fy. Okay, so stress in the reinforcement are going to be 0.87 Fy. Okay, full stress on reinforcement is talking about. Okay, as FD is the 0.87 Fy in case of limit state design. Okay, in case of working stress design it is different, and that we have to check. Okay, I am not writing here. Next, what is B? B is the shear force at the section due to design load. Okay, this B is talking about the shear force. Okay, M1 what? The moment of resistance of the section assuming all the reinforcements are stressed to FD. Okay, basically moment of resistance it is. Okay, now next last part is the L0. L0 is the sum of the anchorage beyond the center of the support and the equivalent anchorage value of any hook or mechanical anchorage at simple support or mechanical anchorage at simple support. At a point of inflection, L0 is limited to the effective depth of the member or 12 phi, whichever is greater. Here phi means diameter of the bar. I will just read this sentence again, how to compute the L0, and we will see it later on in the example also. Sum of the anchorage beyond the center of the support. Suppose in this beam, this is the beam and this is your support. So your bar is continuously coming like that, and it will go like that, and then it can take turn like that, or it can take turn like that. I will tell you what are those things. Okay, so this is the center of support. Okay, so from this what it is saying, sum of the anchorage beyond the center of the support. So beyond the center of the support is talking about support and the equivalent anchorage value of any hook. Okay, this is one hook, this is a U type hook. Okay, any hook or mechanical anchorage at simple support, any type of anchorage we are providing, and at a point of inflection L0 is limited to the effective depth of the member or 12 phi, whichever is greater. Okay, so this wherever point of inflection, in case of point of inflection, this L0 will be limited to maximum D or 12 phi, D or 12 phi, whichever is greater. Okay, so this is how we can decide the value of L0. Next one point is saying that the M1 by MB, whatever it is shown the above in this expression, this M1 by MB, this value can be increased by 30% when the ends of the reinforcements are confined by a compressive reaction. When the ends of the reinforcements are confined by a compressive reaction, this value will be increased by 30%. So in this case, this expression will be written as 1.3. So this expression will be 1.30 M1 by B plus L0. Okay, so equation will be like that. Sorry, this is how we can change the equation. Okay, now what to do in case of negative moment reinforcement? In case of negative moment reinforcement, that is for continuous beam, we can say at least 1/3 of the total reinforcement provided for negative moment at the support shall extend beyond the point of inflection for a distance not less than the effective depth of the member or 12 phi or 1/16th of the clear span, whichever is greater. Okay, so this is the case when we have a negative moment. Generally, at least for this beginning part in our course, we will not be encountering much on negative moments. So, we will be only concentrating on the positive moments bar. Okay. Next, we will see how we will see this that is a close number 26.2.2 anchoring reinforcement bar. We are talking about the anchoring. So, what is those anchoring bar? Okay, how to provide those anchoring bar. Okay. So, next it is talking about the anchoring bars in compression. Okay, as per the codebook, the anchorage length of straight bars in compression shall be equal to the development length of bars in compression as specified in close. That means as specified in clause number 26.2.1 means it is saying that it should be according to the equation, that is LD is equal to phi sigma s divided by 4 tau BD. Okay, as per this guideline we have to calculate it. Okay, so these are a kind of little background on this development length and anchorage length. We will try to take an examples and we will see how whatever we have discussed till now, how we can apply those problems in the example and to get the development length and anchorage length requirements. Okay. So, next slide we will go for the example. Let us say we have a problem. So, in this problem, wait, okay, I will draw the problem and I will come back. Okay, so this is the problem. Say we have a beam whose support is simply supported beam with a width of say 300 mm and the overall depth is 550. Out of that, effective depth is 500 and 550 is the effective cover. So, it is consisting of 4 number of 20 dia reinforcements. Okay. Given factored shear force is 280 kilonewton, and also it says that the width of the column support means where the beam is supporting on the column, that column width is given as 300 mm. Okay. And it is talking about that M20 grade of concrete and Fe415 steel. The question is determine the anchorage length. We need to find out what is the anchorage length required. Okay. So, in this case, first of all, what we have to do? It's talked about Fe415 steel. So, what will be the tau BD? And grade of concrete is M20. So, for M20 grade of concrete, if you refer to the table, tau BD is given as 1.2. But since it is a Fe415 steel, so you have to multiply this by 1.6. It is simply supported beam, so the bottom reinforcement will be under tension, so you need to multiply it by 1.25. So, this value comes out how much? 1.92 MPa. Fine. So, this is okay. Next, we need to find out the development length LD. Okay, what is the formula? Development length LD is equal to phi sigma s divided by 4 tau BD. Okay, I am not writing here the value of phi. Let us say reinforcement diameter is 20. I am just keeping phi as it is. Sigma s is phi s. Sigma s is what I said, 0.87 Fy, 0.87415 divided by 4 into tau BD is how much we have calculated here. Here we have calculated 1.92. So, what is this value? This value comes out 47.015. Phi I am keeping in terms of phi. Let us say it is equation number 1. Okay. Now, we have discussed that what is the requirement of LD. It said that LD when the sigma s is equal to FD should not be more than M1 by V plus L0. Right, few minutes back we have discussed that. Okay. So, now what we need to know? We need to know what is the value of M1. Okay. So, let us to calculate the value of M1, we have to check that whether it is under reinforced or over reinforced sections or not. To do that, okay. So, in this part what we will do? We will do calculation of M1. First of all, we have to check that whether it is a under reinforced or over reinforced. How do we check? We check comparing Cu is equal to TU. Okay, what is CU? CU is equal to 0.36 FCK XUB. What is TU? TU equal to 0.87 FY AST. Okay, so this implies XU is equal to what is available 0.87. FY is how much? 415. What is the AST here? AST here is we have 4 number of 20 dias. So 4 into pi by 4 into 20 square. Can we write? This is divided by 0.36. What is the grade of concrete here given? It is given 20 and B is given to us as 300, better the beam. So if we do this calculation, how much XU is coming? XU is coming here 209.94 mm in case of under reinforced or balanced sections. Okay, next what we have to do, we have to find out the XU max. Okay, let us see what is the XU max. Okay, next we will find out the XU max. Okay, so what we know, XU max by D is equal to 0.48, right, for Fe415 steel. So XU max equal to 0.48 into here D is how much? 300. So 0.48 into D is how much? It was D was 500, B is 300. So D is 500. That means if I multiply this by 500, how much it comes? It comes out 240 mm. Okay, so this is greater than XU, which is 209.94 mm. That means what we can say, it is a under reinforced section. So in case of under reinforced section, we can find out the moment. What will be the MU? MU is equal to, I can use this equation, 0.87 Fy AST D into 1 minus Fy AST by BD FCK. You can use the other equation also, that is MU is equal to 0.36 FCK XU. In that case, XU max we should not use, we should use XU. So anyway, both equations is fine. So what is this? If you calculate this value comes out, use the data, original data. Okay, this value comes out 187.754 kilonewton meter. Okay, so you got the M1 value. Then what was our equation? B value is already given in the equation. BU value is given how much? 280 kilonewton. Factor BU is already given to us. Okay, okay, let us see, there are two things are there. One is whether the reinforcement bars are confined by a compression reactions or tension reinforcement. That is again we have to check it. Okay, let us assume that in this case, because it will be better for us, in this case let us assume that it is the reinforcing bars are confined by compression reinforcement. So we have to increase it by 30%. Okay, so if we increase it by 30%, then what we can write? LD, whatever the value, that must be less than equal to 1.3 M1 by B plus L0. We are assuming here that reinforcing diameter bars are confined by 30%. Okay, so let us put the value. So what is the LD value we have calculated? 47.015. This is equal to 1.3 into, just now we have calculated the M1. What was that? 187.754. So then kilonewton meter, so convert into Newton millimeter, 10 to the power 6 divided by B is how much? 280 kilonewton into 10 to the power 3 Newton. Okay, plus L0. So right now let us assume that L0 is equal to 0. As now I am assuming that L0 is equal to 0. So if you do this calculation, the phi value is saying that phi value must be less than or equal to 18.54 mm. If I do not provide any additional anchorage length, that is L0, then phi value we must be provided, that is less than 18.54 mm. But in the problem already said that we are providing a phi value of 20. Okay, then what I can do, I can, for phi value of 20 I can find out the value of L0. That means the reverse way I can write down. Earlier my equation was the LD is equal to what was that, 1.3 m1 b plus L0. Then I can write what I can write, L0 is equal to what is that, that is LD minus 1.3 m1 divided by b. So LD is how much, 47.01. Let us, since we are using 20 mm, so I am directly writing it as 20 minus 1.3 into m1 we have calculated, what was that, 187.754 into 10 to the power 6 divided by b is how much, 280 into 10 to the power 3. Now if you do this calculation, it's coming L0 is how much, 68.485 mm. Okay, so by this equation we are saying that minimum of L0 beyond the center of the support is to be provided by 68.485. Now we have to check that whether this space is available or not to extend beyond that. How to check that, what should be the value of L0 I can provide. It said that L0, if you just refer to that code book is said that L0 can be taken as a value of whatever the hooks we are providing, that, or it said that limited to effective depth of the member or 12.5, whichever is greater. Okay, so that means what I can say, that L0 is limited to D or 12.5, whichever is greater. In our case D is how much, 500, or 12.5 means 12 into 20. 12 into 20 is how much, 240 or 500. That means I can provide a maximum of 500 mm of L0. L0 means what it is saying, that from the center, beyond the center we have to extend. Okay, suppose this was the beam, originally this was the beam. Okay, and then on that beam there is a support on the column, and that support is how much, 300 mm. Okay, this is the actual column member, actual reinforcements we have provided. Like, now beyond this support we have to provide a minimum value of L0, how much as per our calculation. If you just see the back, that we have to provide a minimum of 68.69 mm. Okay, so now if I extend it, so if it is, this distance is how much, beyond this I have 150 mm. So if the clear cover is 50 mm, then I can provide another 100 mm here. So up to this I can extend, and that is satisfying my L0 criteria. If it is say more than 100 I need, say I need 200 as per this calculation, then what I will do, I will provide a type of hook like that, maybe, or I can provide a hook in this way also. Okay, or I can provide a hook in this. So I can provide this type of hook, I can provide this type of hook. Sorry, I can provide this type of. So depending on the requirement, what type of hook is to be provided, that you have to check. Okay, from the center lines. Okay, so this is how we need to check that whatever by the design we are doing, the anchorage length, that is the additional length, development length, is satisfying or not. Okay, so development length we have to check this for this type of problems. Okay, for any problem, whatever the problems we are doing, we have to check that whether we are proper development length is provided or not, so that the proper bonding will develop. Okay, now since we are providing here L0 is how much, 100, as I said I can provide this. So since 100 we will do this. So now in this equation, if you put 1.3 m1 by b plus L0 value, then this value will be no doubt greater than LD. So what was the equation? Equation say that LD should not be more than this, or it means LD must be less than or equal to this expression. Okay, so basically this LD must be less. So we are getting a LD means here what we are doing a reverse calculation. Okay, and we are finding out that if I provide this value, then it will satisfy the criteria. Okay, so this is how we need to check and we need to do the design problems. Okay, so solve some more problem related to this and practice. Okay, so that's all about the bond, anchorage and development length.